Look up into the sky. Do you understand what is meant by infinity? Why are air molecules in the atmosphere invisible? These are some of the unanswered questions that tell us that there is a limit to human perception of this natural world. Even with the most powerful electron microscope, we cannot see the structure of an atom. We have, however, created models to describe this, such as the planetary model of an atom, which is based on knowledge of our physical world. In this lesson, we will explore whether the microscopic world is behaving in exactly the same way as our physical world. We have developed wave model and particle model of light, which are based on the effects of light and not from direct observation of light itself. We expect these physical models to represent light in its microscopic world. Introduction to Wave-Particle Duality. In this lesson, you will learn to use equation to calculate the Broglie wavelength, describe observations in electron diffraction experiments, explain the advantages of electron microscope. Water waves exhibit reflection, refraction, and interference as does light. Based on this comparison, the wave theory of light was developed. The photoelectric effect experiment leads to the conclusion that light behaves as particles. Each particle contains a quantum of energy or package of energy. What is the name given to a light particle? Answer: photon. What is the expression that defines the energy of a photon? Answer: E equals hf or E equals hc over lambda. In 1923, Louis de Broglie extended the idea of the wave-particle duality of light to material particles. He thought that like light, material particles might also have wave properties. Click the Relativity Theory button for energy-momentum relationship from Relativity Theory. Then click the Momentum of a Photon button. De Broglie proposed that the wavelength of a material particle would be related to its momentum in the same way as the momentum of a photon is related to its wavelength. The wavelength of a material particle is called the de Broglie wavelength. In 1927, C.J. Davison and L.H. Germer succeeded in measuring the wavelength of electrons. In the Davison-Germer experiment, a ray of low-energy electron, 54 electron volts, was incident on nickel crystals. The electrons scattered from the crystals formed a circular diffraction pattern. This observation was previously only observed using waves. It was discovered when X-rays were used instead of electrons. A similar diffraction pattern is produced. Summary: momentum p of a photon is given by p equals h over lambda. Material wavelength, de Broglie wavelength, lambda of a particle is given by lambda equals h over p. The animation shows an electron beam incident normally on a plane of atoms of a metal crystal. The angular diffraction pattern is as shown in the picture on the right. When this diffraction pattern is used to calculate the wavelength, It is found that it agreed with the de Broglie wavelength of the electrons. If the energy of the electrons is 100 electron volts, what is the de Broglie wavelength of the electrons? Click the de Broglie wavelength 1 button. The interatomic spacing of the metal crystal is 0.30 nanometers, and the angle theta for the first order maximum diffraction is 24 degrees. Based on this data, what is the wavelength of the electron? Click the de Broglie wavelength 2 button. What is the de Broglie wavelength of a 20-gram object moving with a speed of 100 meter per second? Is the de Broglie wavelength of this ordinary object significant? Click the answer button. Summary. In the electron diffraction experiment, the de Broglie wavelength lambda of the electron is related to the angle of diffraction theta for the first maximum and is given by d sin theta equals lambda. Understanding of the wave properties of electrons led to the development of the electron microscope. There are two types of electron microscope. The transmission electron microscope produces two-dimensional images, while the scanning electron microscope produces three-dimensional images. The de Broglie wavelength of electrons depends on the accelerating voltage. Electrons are accelerated by voltage of the order of 10 to the power of 5 volts, resulting in wavelength of the order of 10 to the power of minus 12 meter. This produces magnification about 1000 times higher than the optical microscope. The magnification of an electron microscope is about 10 to the power of 4 to 10 to the power of 5. Here we see two electron microscope images. Images are often artificially colored, as seen here, to make the object easier to visualize. The resolution of images formed by optical microscope or electron microscope depends on the wavelength lambda of the light source or the de Broglie wavelength of the electron beam. A shorter wavelength in each case produces an image of higher resolution. Summary. The resolution of image formed by optical microscope or electron microscope depends on the wavelength lambda of the light source or the de Broglie wavelength of the electron beam. The de Broglie wavelength depends on the accelerating voltage. Electrons accelerated by voltage of the order of 10 to the power of 5 volts will have wavelength of the order of 10 to the power of minus 12 meters. The electron microscope has much higher resolution or power than the optical microscope.